Um, um, okay, so you should be able to just see the slides, right? Not my
Yes, just the
presenter view.
slides.
Okay,
Pointers.
perfect. Yeah, so the topic for today is smart pointers. And I mean, I know we've kind of the idea of like a pointer has come up a couple of times, but I haven't really talked too much about it. And I think you've done some lower level languages too, so you probably know what it is. Essentially, it's like a reference to like, here's where this thing's actually stored. But in Rust, there's kind of, oh yeah, sorry. So our learning objectives, so just understand what like a smart pointer is, like what's this distinction, what are the like most commonly used ones, and like when we might want to use them. So really smart pointers are like um there's pointers with a little bit extra functionality. So they might store some additional information or have some other functionality. And then the kind of main ones we'll talk about are the box. Um, and a good time would be on just box itself because it kind of lays some of the groundwork of things that apply to these other types as well. But box and then RC for reference counting, and then ref, mostly ref cell. There's kind of three or four different things in that realm. But I think ref is like the general one. Mostly it'll be like ref cell that we'll talk about. All right, so boxes. So really a box is a way to store data on the heap, to point to data on the heap. So the stack is where things are generally want to be stored, to things that like you kind of um know at compile time because it's faster to read and write. But when you don't know how big something is going to be at compile time, you have to store it on the heap, and that's like a little bit slower to read and write from because it's got to go find a spot of where exactly it can store it, and then it's got to read from kind of a different place. Um, yeah, and so I mean, like a lot of things in Rust, you create it with this method called new, and then you can print out the value. Um,
One thing that could be potentially confusing for people is that B, the variable B there, is stored on the stack. It's the
yes.
five that goes on the heap.
Yeah, the box itself or the
Yeah,
pointer itself is on the
yeah,
stack, but then it just like it's like directs you when you try to
yeah.
get to the value. Um, I don't want to go into these too much, but this is kind of what they give us some of the use cases. So this first case here, we'll see here in a minute. The second one is so we like when you own a value. And like you only care that T implements like a particular trait, but you don't care like a specific type. That's called a trait object. And that will do that in chapter 17, which is like the object-oriented programming features. Um, the third case here is I think the most straightforward. Like you have a lot of data. You might need to have like transfer ownership around, but you don't want to copy everything because it's a lot of data. Box lets you kind of store that data once, and then the things that get copied and change ownership are just the box, the pointer, the small data that's stored on the stack. So one kind of example thing we're going to look at a couple of times here is called a cons list. I think you've done some functional programming, so I'm sure you know what that is. Um, we have it's a list where you have a value and then another list. And so this is kind of like a nested list, right? Where the inner thing here we have three nil, like it could I guess it could be a list or it could be nil, nothing, because there's got to be some terminating point. So that's the element of the first list, and then that next layer of the list holds the value two plus that inner list, and then so on. And so what we were gonna kind of see how boxes work is by implementing sort of a cons list. So in Rust speak, it would look something like this. So we define this as enum because we could have two cases, right? We want to we need to handle the case where there's nothing there, and then the other cases that there is something there. So this enum list refers to itself. In this first variant, we're just writing in for an I32 here, but then that second item in the cons variant is a list, which so that's like that recursive reference, right? You have a list that's within a list. So the problem with that is when the compiler's looking at that, it doesn't understand it like, it's going to see a list within a list within a list. It doesn't see like that sort of stopping point. So it's just kind of it's basically it sees it as like, okay, this is going to take an infinite amount of memory. I can't do that. You need to do something about that. And I did want to show what that looks like. Come on. So when you try to run it, yeah, so it's nice. I mean, it's pretty helpful. It tells you like, hey, this type is recursive. And it's got infinite size. And it suggests to do, a box or an RC or a reference, some of these other things we'll talk about. Um, but the kind of keyword that I want to point out is this indirection. So it's suggesting to us to use some indirection. And what they mean by indirection is effectively like how a pointer works, right? It doesn't directly store that value. It directs you to the value. So there's a little bit of indirection. You're not going to the value directly. You're going through this a pointer. Okay. So since we're talking about boxes, one thing we could do is wrap this list, the inner list in a box, right? So instead of having just the list here, we'll use a box of type list. And so that's kind of our way to similar to the compiler that no, this is, even though it's a recursive type, it's not infinite, because the compiler knows how much memory a box is going to take. So it obviously knows how much an integer I32 is going to take, but then it knows how big a box is going to be, which is just basically it's going to be like an integer, depending on the platform. But then basically it lets us tell the compiler, so you can look at the compiler, like it's okay, this is not infinite. Um, we're not going to have that problem here. Okay, so that's kind of the short and sweet about box. But things that kind of what really part of what makes box a smart pointer is that it has implements these two attributes called deref and drop. And this is for I think all like smart pointers, and we've seen it already before with like references. So these two traits, we're going to kind of talk about what they are and why they're important because it's pretty widely applicable. All right, so it's kind of pretty clear by their name, I think, deref. D uses it basically it implements like the dereference operator. So it can you can customize what happens, like how exactly that dereference works. When it wants to go through a pointer to get the actual value, how does that work? And the kind of cool thing I think about this is as long as you have as long as deref trait is implemented, um, like your code doesn't care whether you have a smart pointer, whether it's a box, whether it's an RC. It's just, like it could be whatever you want as long as it like implements the trait correctly. Which is kind of we've kind of seen that before. It reminds me a little bit of like generics or generic types, generic functions, where you can kind of write things to where you don't have to worry about necessarily the particular type, but that as long as it implements the right trait. So yeah, just a reminder, we use what we've seen before is references. So we use this ampersand before the values. So here y is effectively it's going to be a pointer to the value x. So x has a value, but y doesn't have that value inherently. It has the location of where x is. So to actually retrieve the value, we have to use the star before that. Come on. Close that one. So if you try to remove that star, if you get to put it there, it's going to give you error. Like in this case, it can't compare an integer, which is 5, with um, a reference to an integer. Y is the reference to an integer. In order to get that integer value out, we have to have that star. Okay, so that's what the deref trait does. It kind of tells us how to use that star. How do I apply this star thing? So you use it just like you would in a reference. So in this case, instead of having ampersand x, you just say box x. But here you go, new. I want to create a box that points to the value x, and then you use it the same exact way. So to kind of see a little bit more detail what the trait actually looks like, so we'll implement it on our own here. So we'll have this new type called our box. That's going to be basically a box. So it can take any type t, and it's going to have a tuple holding that t.
Except
Um,
as the text says, it doesn't. We're storing it on the stack, not on the heap.
yes, yes,
It
right.
this one of the when the first time I tried to read this book, I kind of got stuck in this chapter because it turns out the box is like it's like a sort of a pseudo primitive. It's like defined in the Rust source code in the Rust library, but it's also relies on some compiler magic to make it work. So it
Yeah,
always bothered me.
yeah. I think I generally have a gripe with this book. Not a big one, but I think sometimes they just go in a little bit more too much detail than what we need. Um, I think this chapter is a good example of that. There's a lot of stuff that I was really tempted to just cut out because I'm like,
Yeah,
okay, that could be interesting, but that's probably not necessary as an introduction, you know.
yeah,
But
I agree.
in either case, yeah, I think that can make it kind of helps make things a little more confusing than they need to be.
Yeah.
But yeah, so back to our box here, we're going to implement the new method. We want to create a box, and we want to be able to use it just like we could with Rust box. So we create a new one, and then we dereference it with y with asterisk. I didn't want to do that. Okay. Okay. So if we try to run that, we're going to get an error. I believe it shows. Sometimes this Rust playground is a little bit slow. Yeah, so it was going to error saying, "Hey, I don't know how to dereference this. I don't know what star y means. I don't know how to do it in this case." So that's a clue to us that we need to implement the deref trait, which I mean is pretty simple, just like we do for other um, um, for other things we've seen. You do an implementation of deref for our box. Um, this they refer to. We're gonna get to that later. I didn't want to get sidetracked on that, but so just kind of ignore that for now. Um, but to implement this trait, we need a function in here called deref. It takes a reference to self, and then since we stored uh, our box, the value in a tuple, we can go into our box and we get that zeroth first element, zeroth element, whichever one you want to call it. So, we know what our type is like, so we know that's where that value is going to be. We could maybe have a more complex type, or we have two things here, or maybe a struct with um, like named elements. We could have it do that as well. Um, oh, I thought it. Okay, so yeah, so it doesn't print. It's just these assert. So now we can basically we can use it just like we can with box. We can use it just like we can with ampersand. All we have to do is write this, um, implement this trait, and really it all boils down to like just telling Rust like where is this value located within my struct. Um, and so I mean, this is one of the things that I think is kind of useful, but it kind of goes toward that. Are we getting a little too deep into things here? Um, yeah, so Rust has this thing called deref coercion. It's kind of like automatic coercion of types. Like, um, you might see in R when you're com if you combine an integer and a string, the integer is going to get coerced to a string. Um, so basically, this deref coercion is how we can say, okay, I want to create my custom box here, and then I want to use it just like I would like a reference here. Otherwise, we would have to write something more like this, which is a lot more complicated. We'd have to say, use the ampersand to stand still, but then we have dereference them, and it's a lot more. So basically, it uh, makes our life simple and makes things work nicely. All we have to do is do this trait. And then yeah, and then drop is you decide what you want to do when your value is cleaned up. So when you know, a variable inside a function goes out of scope, like what do we want to do with it? And just like with the deref trait, the deref and this deref coercion, Rust is gonna like just do things for you. So you just kind of have to give it the how to do it. So if we wanted to do the trait drop, we need a method or function called lowercase d drop, which is going to take a mutable reference itself. Excuse me. And in this case, like we're just gonna print it out just to show that like something's happening. That's not the one. Did I link? Might have messed up the link here. Oh, or am I clicking the wrong tab? Yeah, I think I messed up the link here, but I think
How do you
you
have
get
your
the idea.
how do you have your tabs on the left like that? That's cool.
What's that?
How do you have your tabs on the left from the
Oh, this is Arc browser, ARC.
Oh, okay, cool.
It's really nice. You can have like spaces down here. So I have it split up to like, okay, this is kind of like my home section. This is like sports.
Oh,
And so it's very, I mean, it does a lot of stuff, but to me, I mostly use it because it's really easy to organize things.
pretty cool. Never even heard of it. Sorry for
Yeah.
the distraction.
No, no problem. Um, so that, implementing this drop trait, Rust will automatically call it whenever your value goes out of scope. We could uh drop things manually as well, if we needed to. But instead of using our drop trait, what we need to do is use this drop function from standard mem. And again, I mean, this is just like a hey, this is nice to know. I
Yeah.
don't think any of us are ever going to get to that point, right? We're not do that kind of program where we really need it, but it's possible.
Well, there's one case where if you're doing interior mutability and you have an immutable borrow, right? And then you want to do a mutable bar after that because you don't need that immutable bar anymore. You can drop the variable that did the because it won't go out of scope otherwise. Unlike an ordinary reference where the compiler can know that you're not using that variable anymore, so the lifetime's over and they'll let you do a mutable immutable borrow again, right?
Yeah.
Uh, for a ref cell, you have to physically tell it, hey, I'm done immutably borrowing this thing by dropping it. And then you can get a immutable borrow. Yeah, I've got those two things confused. You know what I'm
Yeah.
trying
I think I'm thinking of
to
it down. Yeah.
say. Yeah. That's one use case I know for sure with ref cells.
Um, cool. I don't think I really get into that, but that's nice to know.
Yeah.
Um, so the next type or smart pointer type we'll talk about is RC, which the R and C stands for reference counting. And so it's a reference counting pointer. So it allows us to have multiple owners of the same data. And we could do this by counting how many references, how many things, how many owners has. And then when that gets to zero, it basically it can't clean it up until the number of references goes down to zero. Because then it tells it that's how you know, okay, I'm not actually nobody's using it anymore. I can go and clean it up. So yeah, so you kind of could use this if you have some data that you're going to need to access in like different parts of your code base. Um, and you don't know necessarily the order of how things are gonna these other objects or variables are gonna use it. Um, yeah. Yeah, because if we did know if we did know that we could use kind of the normal like borrowing and ownership rules, that last thing to own the data would just be the owner and then um everything else would like borrow. I might be mixing up the terms, but anyways, I think you get the idea.
Yeah.
Um, yeah, and it's I think to kind of relate it a little bit more to this group, R, as I understand it, R uses reference counting like in the like C side of things. So that's how it kind of determines if a copy of a variable needs to be made. So if you only have one um like one instance, your reference count is one on a variable, say, you can it's going to try to modify it in place because it only has one owner. It doesn't have to worry about multiple things trying to change it. But if you have more than one reference, then it knows like, hey, I got, maybe X and Y are looking at this same value. I don't want to I don't want to change it. I'm just going to go to make a copy. And I think the way R works is it just uses like 0, 1 or or many. That's what like advanced R is saying. So it doesn't have a concept of like the actual count, but just like is there zero counts, is there one count, or is there more than one? Um, and I think there is some attempts to kind of change it so it's actually counting things. So I think that would, in theory, that'll minimize the number of like copies you have to, number of times it has to copy things.
Hmm, interesting.
Okay. So going back to that cons list we talked about, um, this is kind of the scenario we're going to model of we have each one of these A, B, and C are cons lists where B and C both contain A as their like second thing. Right, so in other words, A has multiple owners, B and C. So if we could try to do it with boxes, but you know, as you can probably tell, it's not going to work. Um, there, but yeah, so it's not going to work because of the multiple owners issue. So um the actual like cons list, and then this part of the object is going to be owned by like the outer list, and you can't have multiple owners with
Right.
like
It'll be
normal
moved
rules.
into B and then you want to have it for C, basically what you're saying,
Yeah,
right?
yeah. And the books is just like we could use like lifetime parameters. Um, but then you just have to have everything live for like the entire time.
Right.
And to me, that seems like it'd be more complicated to do than it would be, or at least in terms of being able to like read the code. And it's not always going to work. So we can use the reference count instead. So instead of wrapping this internal list in a box, we're going to use an RC smart pointer, so a reference counting smart pointer. So, it has a new method to create it, just like everything else. Um, Specifically, what we're going to use, we use the reference count for the second part of this, so not the value, but like that where potentially a list could be. So the inner list is not gonna have it, right? But then this second layer of the list is gonna have the 10 and then a reference count to, right? So in doing that, we can define B and C to effectively contain A. They can both own A, excuse me, um, by basically it's like a reference to A. So we use this method called RC clone and then pass in A like we would like a reference. Um, the clone doesn't actually clone, doesn't like make a full copy. Um, it just, I mean, it might do a little more, but essentially it just increases the count. They just call it clone. I'm not exactly sure why, but it increases that count. So when we create A, um, well, the count's going to be one, and then when we sorry, when create A, the reference count of A is going to be one, but then when we use it here in B, that's going to be two, and then when we use it here again in C, it's going to be three. And this, like, we can kind of put some principal statements in there to see where things are happening.
Why did it have to have a reference instead of the I was kind of
I'm
surprised.
not sure. Because that's how, I mean, that's just, I guess, how, um,
Huh.
just how like
Oh, right, because you
the
used
API design.
no, I mean no, it does make sense. Because if I passed in A, I would pass ownership of the actual
Yeah.
RC variable, which is not what I want at all.
Yeah,
But
you don't yeah, you don't want the RC,
so
you want the
confusing.
underlying thing. Yeah, this I found this chapter kind of
It
difficult.
is difficult, I agree.
Uh yeah, so if you look at the pre statement, so after creating A, it's one, B, three, and then this is just slightly different. So just having this C in here and this its own little scope here, just to kind of show that like, okay, C is created, it's three, but then after that, once we get to here, we X that C is no longer in scope, it's not living anymore, so then the reference count drops down back down to two.
Right.
And we get these count versus the strong count method. Okay, so that's a reference count. I mean, I think that one's to me is almost like the most straightforward. Um, ref cell, I think, is quite a bit more complicated.
Yes.
So
Then they have
the
RCs of ref cells and ref cells of RCs, and yeah, it gets
yeah,
abused.
yeah. So I think I'm gonna try to just go over this a little more quickly because again, I don't see. I mean, I'm sure that this is like a nice to know, but I think our use cases we're probably not gonna need to know very in depth of like all these weird combinations. Um, but like kind of one use case they give is you can have that immutable reference to mutable data, which to me is kind of like a private field in an object, right? And like a um, object-oriented language. It's something that can change internally, but you can't change it from the outside. Which I mean, essentially, it's good in the because it lets you control everything. You don't have to worry about the user doing something weird. So yeah, rust cell is a smart pointer where borrowing rules are enforced at runtime instead of compile time. So it's kind of a way to get around the compiler thing, but you have to do a little more management of it because the compiler can't do it. But then there's also a risk there because the rules are enforced at runtime. Um, Rust can't really do anything but panic unless
Right.
if something goes wrong. Oh, yeah, I forgot I had things here, but yeah, all right, so we implement that interior mutability pattern. I like this way of the book says is a mutable memory location with dynamically checked borrower rules. So on the fly or, during runtime. Okay, so let's look at that interior mutability pattern. All right, so the example we're going to use is we're going to pretend we have an API, okay, and we want to write a Rust library that keeps track of how many API calls a user has made relative to like the total number they can make in a day. So if you only get 100 calls per day, as you're hitting, every time you call the API, I want to check to see where you are against that 100. So that's kind of the motivation for this. Um, that's the library, but like good developers, yeah, so we're gonna track that. Um, and then we'll send we have the ability to send a message saying like where you are relative to the total. So not going to actually do that because it would be up to the user to determine how they want to send it. Like maybe it's an email, maybe they send it off to another API or something like that, like internally. So we just kind of implement the message, and then we'll basically like give them a trait that they would have to
Yeah.
implement.
It's like a dependency injection type thing, right?
Yeah. And the kind of we're ultimately going to get to the key thing though is like good developers, we want to write tests. Um, the way we can test that is by creating this mock object. So basically implementing this messenger trait for sending the message in a mocked way where we're not actually going to send anything, but we still need to be able to test out the functionality. Okay, so we'll create a struct called limit tracker. It's going to have like the messenger object of the value. So this is what like the current number of calls are, and then the total maximum number of calls. Okay, and so we're gonna implement some functions for this limit tracker. We I think we saw this a couple of weeks ago with I forget what section it was, but anyways, what we're saying here is that the limit tracker it takes the type T here has to implement this messenger trait that we'll see in a second. But we want to make a new method, and these are all going to be public because we want to be able to expose it to the user. So with the new method, we just take the information and we create it. Okay, so initial value is going to be 0, which makes sense. And then max, maybe we want to change that depending on who the customer is. Then all we're really going to write is the set value. So um, given a value, we're gonna update the value, right? So every time we make a call, we're gonna say, hey, set the value one higher. And the message is gonna take the form of we're gonna see how far you are relative to the max. So if you're over, or at least equal to the max, right? So if you're at 100% of the max, you say, hey, like you're over your quota, we can't run and you can't use this service anymore. And then they've got like 90% and 75% as like a warnings like, hey, you're getting closer. Um, be mindful you're close to your limit. Okay. And then we have the trait messenger that we're going to expose to the user right now, and then it needs to have a send function. So it doesn't really do anything now, but like this is
And
what
the
the user's going to have to kind of fill in.
And the
effectively
key
filling that
thing,
part.
yeah, and the key thing is that send takes a reference to an immutable self.
Yes.
So,
Yeah, because so from the user perspective, it's going to be immutable, but we want to be able to do is internally
log
mute
it.
it.
Yeah, yeah.
All right. So yeah, like good developers, we want to write some tests. So we'll create this struct called mock messenger, and really we're just gonna have this vector that's gonna we're gonna push to that vector to store any messages rather than like sending them through email. Now since we have this struct, okay, we need to implement our um, we need to be able to create a new one, and then we need to implement the messenger trait. So what we want to do is take this vector of messages and just add to it, right? So um, every time we send, we're going to send it to this vector, right? And then the actual test is really just hey, make sure that when you get to 75%, you get the warning, right? So we'll say the limit is 100, and what happens when we set the value at 80, we expect that 75% message to show up. And then not really checking the message here, just kind of the length, like, hey, we only have this one test, so when we add it, we expect it to have length one.
Right.
Um, Unfortunately, that will not work because we can't borrow that set messages vector as mutable, right? We want to keep though the only way we could do that is we'd have to like change the signature of our send method, but we don't want to do that. We want to keep it immutable. So that's where a ref cell comes in handy. So this is not included in the prelude, so we do have to um pull it in with a use statement, which kind of to me signals it's not as common as like box, right? But just like we did before, instead of having this vector, we're gonna wrap it in ref cell, and that's gonna make it mutable. So, when we initialize, we're just gonna instead of having just the vec, we need to wrap it in ref cell new. And then what gets a little bit different in this case is we have that ref cell, with our vector. We're going to call this method borrow mute. And then so we're borrowing, I want to borrow it as a mutable thing, and then I want to push to it. And similarly, but when we actually check the value here in the test, we don't need to change it in this case, so we just want to borrow. So borrow would be borrowing immutably, and then borrow mute is borrow mutably. Which one is that? Yeah, this one. So it lets us change this messages for testing, just for testing purposes. Yeah, and we can see it passed. So I feel like that's one thing I found interesting is like there's kind of a different syntax for this, right? Box, you kind of use almost the same syntax as we do
Yeah, I
for
mean
like references.
yeah, it's a function call. I mean, it's a method
Yeah.
on the thing, and it's actually like implemented in Rust in the library. It just uh calls some unsafe code that we're allowed to do borrowing things.
Yeah.
How it works beyond that, I don't really know. But
Yeah.
they pointed to the rust01 where they call it to find out more at the end of this chapter.
Yeah, I saw that and it's like that's interesting book. Like, here's how to do things you shouldn't do in
Yeah.
Rust. Um, and the name is perfect too.
Yeah, it is.
But yeah, and I think we've kind of been looking at these smart pointers in isolation, but we can combine them. So a common pattern that they say like often used in Rust is when you combine a ref cell with a reference count, you could have both mutable data via the ref cell and multiple owners via the reference counting. So you can have that internal mutability with multiple owners. So that cons list we had before, we have list B and C that um, like own A. Um, RC lets us have lets us have that multiple owners of A, B, and C. Um, but the lists are immutable in that case. Like we can't once we create them, like that's it, they're fixed. But by combining it with ref cell, we can keep that multiple owners, but then we can have the list be mutable. So what we would do is take our reference count and get it backwards. Okay, so we have the value we want, we wrap that in a ref cell, and then we wrap that ref cell in an RC, and then so that's kind of a big difference here, right? Instead of just having the I32, and then we use a ref cell for the second part of our list. Um, I'm not going to go through all of these in detail. I did put links to like almost every stage. So almost every code example has a link where you can kind of see how things are happening. But yeah, when we create a new one, we have to create called ref cell and RC. Like we saw before when we clone, we take a reference to A. We can um, dereference it and borrow it mutably and change it. So it's actually kind of interesting if you, well, maybe I should just run this one. You run this one, you can see that, you see how the values change. So
Yeah.
let me see. So you can see A now has the value 15. You can see all this value everywhere is 15. Almost like it almost feels like to me like reactivity in Shiny, where you can change it here without having to kind of rewrite everything. It's gonna change it in the other anywhere that's used. But unfortunately, you can have like it's possible to get memory leaks with this, and essentially you get like a cyclic dependency. Um, and this is kind of an example they're showing where you could set it up to where you have a cons list A that references a cons list B and a cons list B that references A. And I don't Yeah, I think I don't have the code, but I do have some code in here. I think it's worth pointing out because I was a little bit confused about this first of like what are you even talking about? So you create this cons list A, and then you take B, which references A. But then a little bit later, you take that second part of A, that list part and not the value part, and you put in a reference to B. So that's where you get this like loop. And I don't care about those. Oh, maybe this is the working version, sorry. But anyways, yeah, you can get this like cycle and that's so
Right.
it'll lead to memory leaks because you're still you still have your reference count. Your reference count is never going to get to zero because they don't refer to each other. So I guess like, you could do something you mentioned earlier where you can manually drop them if you know you're kind of in that scenario, but um I would think you'd want to avoid that scenario.
Right. Yeah, that sounds dangerous.
Yeah. So what we could do is use yet another smart pointer called weak for a weak reference. And it kind of doesn't have like the same kind of ownership rules relationship. Um, it's like an RC, but it affects the weak count of a RC. And so strong count is what we saw before. That's like kind of the true count. But then there's also this concept of a weak count where that weak count doesn't have an effect on like the ownership and it doesn't have an effect when like something is cleaned up when it goes out of scope. So as long as your strong count is zero, it doesn't matter where your weak count, I can still you can still release it. Right. So this is kind of the last example is if you think of like a tree, right? So maybe you want to have a tree data structure where any given node can reference both its parent on that tree and any children that it has. Um, so to implement, so that's definitely, I mean, that's going to be a cyclic thing, right? So to make sure we don't do that, and don't have memory leaks, we can use a weak reference. We can use a ref cell, an RCs, and weeks, and we can just combine all this stuff together. Um, so we can't really use RC because then we would have that reference cycle between like the parent, um, a node's parent and the node's children. But if we use a weak reference, um, for the parent and the RC reference for the child, what this gives us is that uh, a parent node will own its child nodes, but not like vice versa, which is the direction we really care about because if I remove a parent from the tree, all its children should be removed. But if I remove one child, it shouldn't remove the parent and because it could be removing its siblings as well.
Well, that's a confusing type, huh? So
Yeah.
the type of children is a ref cell because we want to be able to potentially modify interiorly, I guess, the
hmm
for whatever reason. I don't know why it has to be interior mutability on that, but the children. And then it's a vector, no, the children, and then it's a vector because they have multiple children, and each of those children is an RC node, a reference
Yeah.
counted node.
Yeah.
Interesting.
And it's got the recursiveness going on.
Yeah.
It's got a little bit of everything here,
Yeah. I wonder why it has to be a ref cell
which
though.
is wow.
I get the ref cell for the parent, but
Yeah.
although it could still be just using
Well,
it directly, right? I don't know if you need interior mutability here. I can't remember why they said that.
I don't
It may
remember.
be obvious as you go on. I don't know. I just can't remember.
Yeah, I honestly I don't remember. At this point, I was just like,
Yeah,
okay,
you
if you
get
say so.
this chapter wears you down, man.
Yeah,
It wears you down. I
I
got
had
some.
to. I split it over like several days too. Like, just okay,
You're like,
okay.
no, no more. There's another section. Oh man. Yeah.
Yeah, okay. So yeah, like you have the vector in here, um, and then you have, we initialize it with no children. Actually, let me show. This is an example, and it kind of shows you how this works. I just cut out a lot of it. Okay. Ref cell, wrapping a vec, wrapping an RC, wrapping a node here. And I'm not going to go through this, but it's worth taking a look at this because they basically add print statements. So you can kind of see what's the strong count of this, what would be a leaf node, and what's the weak count. And you can kind of see how it's changing as as you
Yeah.
change things in the program, right? To take the leaf, get the parent out of it, and then do a mutable borrow, and like this downgrade takes it from a strong, like a RC strong count to like a weak reference. There's a lot going on, but it gives you kind of walks you through if you follow the code and look at the output at the same time. It's helpful to kind of trace what's happening and how these things work. Okay, so I really like this kind of. It wasn't the last part of the book, but it gives you it gives I think a better overview than did at the beginning of like basically like the features that one has over the other and kind of when you want to use one of these types over the other. So I'm not going to read them, but it's worth kind of looking at. I think it kind of gives you a good summary of all these different types.
Oh, but you just said RC it says right there RC allows only immutable borrows, so we do need to wrap a ref cell to be able to do that, even though we don't necessarily need the interior part, but we kind of do. Very strange. Interesting. Huh.
There we go.
Cool. You made it just